Aircraft welding. Introduction. Welding can be traced back to the Bronze Age, but it was not until the 19th century that welding as we know it today was invented. Some of the first successful commercially manufactured aircraft were constructed from welded steel tube frames. As the technology and manufacturing processes evolved in the aircraft and aerospace industry, lighter metals such as aluminum, magnesium, and titanium were used in their construction. New processes and methods of welding these metals were developed. This chapter provides some of the basic information needed to understand and initiate the various welding methods and processes. Traditionally, welding is defined as a process that joins metal by melting or hammering the workpieces until they are united together. With the right equipment and instruction, almost anyone with some basic mechanical skill, dexterity, and practice can learn to weld. There are three general types of welding: gas, electric arc, and electric resistance. Each type of welding has several variations, some of which are used in the construction of aircraft. Additionally, there are some new welding processes that have been developed in recent years that are highlighted for the purpose of information. This chapter addresses the welding equipment, methods, and various techniques used during the repair of aircraft and fabrication of component parts, including the processes of brazing and soldering with various metals. Types of welding. Gas welding. Gas welding is accomplished by heating the ends or edges of metal parts to a molten state with a high temperature flame. The oxyacetylene flame, with a temperature of approximately 6,300 degrees Fahrenheit, is produced with a torch, burning acetylene and mixing it with pure oxygen. Hydrogen may be used in place of acetylene for aluminum welding, but the heat output is reduced to about 4,800 degrees Fahrenheit. Gas welding was the method most commonly used in production on aircraft materials under 3/16 inch in thickness until the mid 1950s, when it was replaced by electric welding for economic reasons. Gas welding continues to be a very popular and proven method for repair operations. Nearly all gas welding in aircraft fabrication is performed with oxyacetylene welding equipment consisting of two cylinders, acetylene and oxygen, acetylene and oxygen pressure regulation, and cylinder pressure gauges, two lengths of colored hose, red for acetylene and green for oxygen, with adapter connections for the regulators and torch. A welding torch with an internal mixing head, various size tips, and hose connections. Welding goggles fitted with appropriate colored lenses. A flint or spark lighter. Special wrench for acetylene tank valve if needed. An appropriately rated fire extinguisher. The equipment may be permanently installed in the shop, but most welding outfits are of the portable type. Electric arc welding. Electric arc welding is used extensively by the aircraft industry in both the manufacture and repair of aircraft. It can be used satisfactorily to join all weldable metals provided that the proper processes and materials are used. The four types of electric arc welding are addressed in the following paragraphs. Shielded metal arc welding. Shielded metal arc welding is the most common type of welding and is usually referred to as stick welding. The equipment consists of a metal rod and coated with a welding flux that is clamped in an electric holder that is connected by a heavy electrical cable to a low voltage and high current in either alternating or direct current, depending on the type of welding being done. An arc is struck between the rod and the work and produces heat in excess of 10,000 degrees Fahrenheit, which melts both the material and the rod. The welding circuit consists of a welding machine, two leads, an electrode holder, an electrode, and the work to be welded. When the electrode is touched to the metal to be welded, the circuit is complete and the current flows. The electrode is then withdrawn from the metal approximately a quarter inch to form an air gap between the metal and the electrode. If the correct gap is maintained, the current bridges the gap to form a sustained electric spark called the arc. This action melts the electrode and the coating of flux. As the flux melts, it releases an inert gas that shields the molten puddle from oxygen in the air to prevent oxidation. The molten flux covers the weld and hardens to an airtight slag that protects the weld bead as it cools. Some aircraft manufacturers, such as Stinson, use this process for the welding of 4130 steel fuselage structures. This was followed by heat treatment in an oven to stress relieve and normalize the structure. Shown in figure 5.3 is a typical arc welding machine with cables, ground clamp, and electrode holder. Gas metal arc welding. Gas metal arc welding was formerly called metal inert gas welding, MIG welding. It is an improvement over stick welding because an uncoated wire electrode is fed into and through the torch and an inert gas such as argon, helium, or carbon dioxide flows out around the wire to protect the puddle from oxygen. The power supply is connected to the torch and the work, and the arc produces the intense heat needed to melt the work and the electrode. Low voltage, high current DC is typically used with gas metal arc welding. Figure 5.5 shows the equipment required for the typical MIG welding setup. This method of welding can be used for large volume manufacturing and production work. It is not well suited to repair work because the weld quality cannot be easily determined without destructive testing. Figure 5.6 depicts a typical power source for MIG welding. Gas tungsten arc welding. Gas tungsten arc welding is a method of electric arc welding that fills most of the needs in aircraft maintenance and repair when proper procedures and materials are used. It is the preferred method to use on stainless steel, magnesium, and most forms of thick aluminum. It is more commonly known as tungsten inert gas welding, and by the trade names of HeliArc and HeliWeld. These names were derived from the inert helium gas that was originally used. The first two methods of electric arc welding that were addressed used a consumable electrode that produced a filler for the weld. In TIG welding, the electrode is a tungsten rod that forms the path for the high amperage arc between it and the work to melt the metal over 5400 degrees Fahrenheit. The electrode is not consumed and used as filler, so a filler rod is manually fed into the molten puddle in almost the same manner as when using an oxyacetylene torch. A stream of inert gas, such as argon or helium, flows around the electrode and envelopes the arc, thereby preventing the formation of oxides in the molten puddle. The versatility of a TIG welder is increased by the choice of the power supply being used. DC of either polarity or AC may be used. Either select the welder setting to DC straight polarity when welding mild steel, stainless steel, and titanium, or select AC for welding aluminum and magnesium. Figure 5.9 is a typical power source for TIG welding along with a torch, foot-operated current control, regulator for inert gas, and assorted power cables. Electric resistance welding. Electric resistance welding, either spot welding or seam welding, is typically used to join thin sheet metal components during the manufacturing process. Spot welding. Two copper electrodes are held in the jaws of the spot welding machine, and the material to be welded is clamped between them. Pressure is applied to hold the electrodes tightly together, and electrical current flows through the electrodes in the material. The resistance of the material being welded is so much higher than that of copper electrodes that enough heat is generated to melt the metal. The pressure on the electrodes forces the molten spots in the two pieces of metal to unite, and this pressure is held after the current stops flowing long enough for the metal to solidify. The amount of current, pressure, and dwell time are all carefully controlled and matched to the type of material and the thickness to produce the correct spot welds. Seam welding. Rather than having to release the electrodes and move the material to form a series of spot welds, a seam welding machine is used to manufacture fuel tanks and other components where a continuous weld is needed. Two copper wheels replace the bar-shaped electrodes. The metal to be welded is moved between them, and electric pulses create spots of molten metal to overlap to form the continuous seam. Plasma arc welding. Plasma arc welding was developed in 1964 as a method of bringing better control to the arc welding process. Plasma arc welding provides an advanced level of control and accuracy using automated equipment to produce high-quality welds. In miniature and precision applications, furthermore, plasma arc welding is equally suited to manual operation and can be performed by a person using skills similar to those for gas tungsten arc welding. In the plasma welding torch, a non-consumable tungsten electrode is located within a fine-bore copper nozzle. A pilot arc is initiated between the torque electrode and nozzle tip. This arc is then transferred to the metal being welded. By forcing the plasma gas and arc through a constricted orifice, the torch delivers a high concentration of heat to a small area. The plasma process produces exceptionally high-quality welds. Plasma gas is normally argon. The torch also uses a secondary gas, such as argon helium or argon nitrogen, that assist in shielding the molten weld puddle and minimizing oxidation of the weld. Like gas tungsten arc welding, the plasma arc welding process can be used to weld most commercial metals and it can be used for a wide variety of metal thicknesses. On thin material from foil to an eighth inch, the process is desirable because of the low heat input. The process provides relatively constant heat input because arc length variations are not very critical. On material thicknesses greater than an eighth inch and using automated equipment, a keyhole technique is often used to produce full penetration single path welds. In the keyhole technique, the plasma completely penetrates the workpiece. The molten weld metal flows to the rear of the keyhole and solidifies as the torch moves on. The high quality weld produces arc characterized by deep, narrow penetration and a small weld face. When plasma arc welding is performed manually, the process requires a high degree of welding skills similar to that required for gas tungsten arc welding. However, the equipment is more complex and requires a high degree of knowledge to set up and use. The equipment required for plasma arc welding includes a welding machine, a special plasma arc control system, a plasma welding torch, water cooled, the source of plasma, and shielding gas, and filler material when required. Because of the cost associated with this equipment, this process is very limited outside of manufacturing facilities. Plasma arc cutting. When a plasma cutting torch is used, the gas is usually compressed air. The plasma cutting machine works by constricting an electric arc in a nozzle and forcing the ionized gas through it. This heats the gas that melts the metal, which is blown away by the air pressure. By increasing air pressure and intensifying the arc with higher voltages, the cutter is capable of blasting through thicker metals and blowing away the dross with minimum cleanup. Plasma arc systems can cut all electrically conductive metals, including aluminum and stainless steel. These two metals can be cut by oxy-fuel cutting systems because they have an oxide layer that prevents oxidation from occurring. Plasma cutting works well on thin metals and can successfully cut brass and copper in excess of 2 inches thick. Plasma cutting machines can rapidly and precisely cut through, gouge, or pierce any electrically conductive metal without preheating. The plasma cutter produces a precise curve with a small heat affected zone that prevents warping and damage. Gas welding and cutting equipment. Welding gases. Acetylene. This is the primary fuel for oxy-fuel welding and cutting. It is chemically very unstable and is stored in special cylinders designed to keep the gas dissolved. The cylinders are packed with a porous material and then saturated with acetone. When the acetylene is added to the cylinder, it dissolves. In this solution, it becomes stable. Pure acetylene stored in a freeze state explodes from a slight shock at 29.4 pounds per square inch. The acetylene pressure gauge should never be set higher than 15 psi for welding or cutting. Argon. Argon is a colorless, odorless, tasteless, and non-toxic inert gas. Inert gas cannot combine with other elements. It has a very low chemical reactivity and low thermal conductivity. It is used as a gas shield for the electrode and MIG-TIG in plasma welding equipment. Helium. Helium is a colorless, odorless, tasteless, and non-toxic inert gas. Its boiling and melting point are the lowest of the elements and normally exists only in gas form. It is used as a protective gas shield for many industrial uses, including electric arc welding. Pressure regulators. A pressure regulator is attached to a gas cylinder and is used to lower the cylinder pressure to the desired working pressure. Regulators have two gauges, one indicating the pressure in the cylinder and the second showing the working pressure. By turning the adjustment knob in or out, a spring operating a flexible diaphragm opens and closes a valve in the regulator. Turning the knob in causes the flow and pressure to increase. Backing it out decreases the flow and pressure. There are two types of regulators, single and two-stage. They perform the same function, but the two-stage regulator maintains a more constant outlet pressure and flows as the cylinder volume and pressure drops. Two-stage regulators can be identified by a larger second pressure chamber under the regulator knob. Hydrogen. Hydrogen is a colorless, odorless, tasteless, and highly flammable gas. It can be used at a higher pressure than acetylene and is used for underwater welding and cutting. It also can be used for aluminum welding using the oxyhydrogen process. Oxygen. Oxygen is a colorless, odorless, and non-flammable gas. It is used in the welding process to increase the combustion rate, which increases the flame temperature of flammable gas. Welding hose. A welding hose connects the regulators to the torch. It is typically a double hose joined together during manufacture. The acetylene hose is red and has left-hand threads indicated by a groove cut into the connection net. The oxygen hose is green and has right-hand threads indicated by the absence of a groove on the connection net. Welding hoses are produced in different sizes from quarter-inch to half-inch inside diameter. The hose should be marked for light, standard, and heavy-duty service, plus a grade indicating whether it has an oil or flame-resistant cover. The hose should have the date of manufacture, maximum working pressure of 200 psi, and indicate that it meets specification IP90 of the Rubber Manufacturers Association and the Compressed Gas Association for rubber welding hoses. Grade R hose should only be used with acetylene gas. A T-grade hose must be used with propane, MAP, and all other fuel gases. Check valves and flashback arresters. The check valve stops the reverse flow of the gas and can be installed either between the regulator and the hose or the hose and the torch. Excessive overheating of cutting, welding, and heating tips can cause flashback conditions. A flashback can be caused when a tip is overheated and the gas ignites before passing out of the tip. The flame is then burning internally rather than on the outside of the tip and is usually identified by a shrill hissing or squealing noise. A flashback arrestor installed on each hose prevents a high-pressure flame or oxygen-fuel mixture from being pushed back into either cylinder, causing an explosion. The flashback arresters incorporate a check valve that stops the reverse flow of gas in the advancement of a flashback fire. Torches. Equal pressure torch. The equal pressure torch is the most commonly used torch for oxyacetylene welding. It has a mixing chamber and uses acetylene fuel at 1 to 15 psi. The flame is easy to adjust and there is less chance of flashback with this torch. There are several small lightweight torches of this type that are ideal for aviation welding projects. The Smith Airline and the Mecco Midget torches are small enough to be used in closed confined areas, lightweight enough to reduce fatigue during long welding sessions, yet with the appropriate tips are capable of welding quarter-inch steel. Injector torch. The injector torch uses fuel gas at pressures between just above 0 and 2 psi. This torch is typically used with propane and propylene gas. High pressure oxygen comes through a small nozzle inside the torch head and pulls the fuel gas along it via a Venturi effect. The low pressure injector torch is more prone to flashback. Cutting torch. The cutting torch is an attachment added to the torch handle that allows the cutting of metal. The cutting process is fundamentally the rapid burning or oxidizing of the metal in a localized area. The metal is heated to a bright red color, which is the kindling temperature using only the preheat jets. Then a jet of high-pressure oxygen released by the lever on the cutting attachment is directed against the heated metal. This oxygen blast combines with the hot metal and forms an intensely hot oxide. The molten oxide is blown down the sides of the cut, heating the metal in its path to the kindling temperature as the torch is moved along the line of the desired cut. The heated metal also burns to an oxide that is blown away on the underside of the piece. Torch tips. The torch tip delivers and controls the final flow of gases. It is important that you use the correct tip with the proper gas pressures for the work to be welded satisfactorily. The size of the tip opening, not the temperature, determines the amount of heat applied to the work. If an excessively small tip is used, the heat provided is insufficient to produce penetration to the proper depth. If the tip is too large, the heat is too great, and holes are burned in the metal. Torch tip sizes are designed by numbers. The manufacturer can provide a chart with recommended sizes for welding specific thicknesses of metal. With use, a torch tip becomes clogged with carbon deposits. If it is allowed to contact the molten pool, particles of slag may clog the tip. This may cause a backfire, which is a momentary backward flow of the gases at the torch tip. A backfire is rarely dangerous, but molten metal may be splattered when the flame pops. Tips should be cleaned with the proper size tip cleaner to avoid enlarging the tip opening. Welding eyewear. Protective eyewear for use with oxy-fuel welding outfits is available in several styles and must be worn to protect the welder's eyes from the bright flame and flying sparks. This eyewear is not for use with arc welding equipment. Some of the styles available have individual lenses and include goggles that employ a headpiece and an elastic head strap to keep them snug around the eyes for protection from the occasional showering spark. Another popular style is the rectangular eye shield that takes a standard 2-inch by 4¼ inch lens. This style is available with an elastic strap but is far more comfortable and better filling when attached to a proper fitting adjustable headgear. It can be worn over prescription glasses, provides protection from flying sparks, and accepts a variety of standard shade and color lenses. A clear safety glass lens is added in front of the shaded lens to protect it from damage. It was standard practice in the past to select a lens shade for gas welding based on the brightness of flame emitting from the torch. The darkest shade of lens showing a clear definition of the work was normally the most desirable. However, when flux was used for brazing and welding, the torch heat caused the sodium in the flux to give off a brilliant yellow-orange flare, hiding a clear view of the weld area and causing many eye problems. Various types of lens and colors were tried for periods of time without much success. It was not until the late 1980s that TM Technologies developed and patented a new green glass designed especially for aluminum oxyfuel welding. It not only eliminated the sodium orange flare completely, but also provided the necessary protection from ultraviolet, infrared, and blue light and impact to meet the requirements of the American National Standards Institute ZA7 1989 safety standards for a special purpose lens. This lens can be used for welding and brazing all metals using an oxyfuel torch. Torch lighters Torch lighters are called friction lighters or flint strikers. The lighter consists of a file-shaped piece of steel, usually recessed in a cup-like device, and a replaceable flint, which, when drawn across the steel, produces a shower of sparks to light the fuel gas. An open flame or match should never be used to light a torch because accumulated gas may envelope the hand and, when ignited, cause a severe burn. Filler rod. The use of the proper type of filler rod is very important for oxyacetylene welding. This material adds not only reinforcement to the weld area, but also desired properties to the finished weld. By selecting the proper rod, tensile strength or ductility can be secured in a weld. Similarly, the proper rod can help retain the desired amount of corrosion resistance. In some cases, a suitable rod with a lower melting point helps to avoid cracks caused by expansion and contraction. Welding rods may be classified as ferrous or non-ferrous. Ferrous rods can include carbon alloy steel rods as well as cast iron rods. Non-ferrous rods include brass, aluminum, magnesium, copper, silver, and their various alloys. Welding rods are manufactured in standard 36-inch lengths and in diameters from 16th inch to 3/8 inch. The diameter of the rod to be used is governed by the thickness of the metals to be joined. If the rod is too small, it cannot conduct heat away from the puddle rapidly enough, and a burned hole results. A rod too large in diameter draws heat away and chills the puddle, resulting in poor penetration of the joined metal. All filler rods should be cleaned prior to use. Equipment setup. Setting up acetylene welding equipment in preparation for welding should be accomplished in a systematic and definite order to avoid costly damage to equipment and compromising the safety of personnel. Gas cylinders. All cylinders should be stored and transported in the upright position, especially acetylene cylinders, because they contain an absorbent material saturated with liquid acetone. If the cylinder were laid on its side, allowing the acetone to enter and contaminate the regulator, hose, and torch, fuel starvation and a resultant flashback in the system could result. If an acetylene cylinder must be placed on its side for a period of time, it must be stored in the upright position for at least twice as long as before being used. Gas cylinders should be secured using, usually with a chain, in a permanent location or in a suitable mobile cart. The cylinder's protective steel cap should not be removed until the cylinder is put into service. Regulators. Prior to installing the regulator on a gas cylinder, open the cylinder shutoff valve for an instant to blow out any foreign material that may be lodged in the outlet. Close the valve and wipe off the connection with a clean, oil-free cloth. Connect the acetylene pressure regulator to the acetylene cylinder and tighten the left-hand nut. Connect the oxygen pressure regulator to the oxygen cylinder and tighten the right-hand nut. The connection fittings are brass and do not require a lot of torque to prevent them from leaking. At this time, check to ensure the adjusting screw on each pressure regulator is backed out by turning counterclockwise until it turns freely. Hoses. Connect the red hose with the left-hand threads to the acetylene pressure regulator and the green hose with the right-hand threads to the oxygen pressure regulator. This is the location between the regulator and hose in which flashback arresters should be installed. Again, because the fittings are brass and easily damaged, tighten only enough to prevent leakage. Stand off to the side, away from the face of the gauges. Now very slowly open the oxygen cylinder valve and read the cylinder gauge to check the contents of the tank. The oxygen cylinder shutoff valve has a double C valve. It should be fully opened against the stop to seat the valve and prevent a leak. The acetylene cylinder shutoff valve should be slowly opened, just enough to get the cylinder pressure reading on the regulator, and then one half of a turn more. This allows a quick shutoff if needed. As a recommended safety practice, the cylinder should not be depleted in content below 20 psi. This prevents the possible reversal of gas from the opposite tank. Both hoses should both hoses should be blown out before attaching to the torch. This is accomplished for each cylinder by turning the pressure adjusting screw in clockwise until the gas escapes, and then quickly backing the screw out to shut off the flow. This should be done in a well-ventilated open space, free from sparks, flames, or other sources of ignition. The connecting torch. Connect the red hose with the left-hand thread connector nut to the left-hand thread fitting on the torch. Connect the green hose with the right-hand thread connector nut to the right-hand thread fitting on the torch. Cross the valves on the torch handle and check all connections for leaks as follows. Turn in the adjusting screw in the oxygen pressure regulator until the working pressure indicates 10 psi. Turn in the adjusting screw in the acetylene pressure regulator until the working pressure indicates 5 psi. Back both adjusting screws of the regulators and verify that the working pressure remains steady. If it drops and the pressure is lost, a leak is indicated between the regulator and the torch. A general tightening of all connections should fix a leak. Repeat a check of the system. If a leak is still indicated by a loss in the working pressure, a mixture of soapy water on all connections reveals the source of the leak. Never check for a leak with a flame, because a serious explosion could occur. Select the tip size. Welding and cutting tips are available in a variety of sizes for almost any job and are identified by number. The higher the number, the bigger the hole in the tip, allowing more heat to be directed onto the metal and allowing thicker metal to be welded or cut. Welding tips have one hole and cutting tips have a number of holes. The cutting tip has one large hole in the center for the cutting oxygen and a number of smaller holes around it that supply fuel gas and oxygen for the preheating flame. The selection of the tip size is very important, not only for the quality of the weld or the efficiency of the cutting process, but for the overall operation of the welding equipment and safety of the personnel using it. Starvation occurs if torch tips are operated at less than the required volume of gas, leading to tip overheating and possible flashbacks. Incorrect tip size and obstructed tip orifices can also cause overheating and flashback conditions. All fuel cylinders have a limited capacity to deliver gas to the tip. That capacity is further limited by the gas contents remaining in the cylinder and the temperature of the cylinder. The following provide some recommended procedures to guard against overheating and flashbacks. Refer to the manufacturer's recommendations for tip size based on the metal's thickness. Use the recommended gas pressure settings for the tip size being used. Provide the correct volume of gas as recommended for each tip size. Do not use an excessively long hose, one with multiple splices, or one that may be too small in diameter and restrict the flow of gas. Note, acetylene is limited to a maximum continuous withdrawal rate of 1/7 of the cylinder's rated capacity when full. For example, an acetylene cylinder that has a capacity of 330 cubic feet has a maximum withdrawal of 47 cubic feet per hour. This is determined by dividing 330 by 7. As a safety precaution, it is recommended that flashback arresters be installed between the regulators and the gas supply hoses of all welding outfits. Figure 521 shows recommended tip sizes of different manufacturers for welding various thickness of metals. Adjusting the regulator working pressure. The working pressure should be set according to the manufacturer's recommendation for the tip size that is being used to weld or cut. This is a recommended method that works for most welding and cutting operations. In a well-ventilated area, open the acetylene valve on the torch and turn the adjusting screw on the acetylene pressure regulator clockwise until the desired pressure is set. Close the acetylene valve on the torch, then set the oxygen pressure in the same manner by opening the oxygen valve on the torch and turning the adjusting screw clockwise on the oxygen regulator until desired pressure is set. Then close the oxygen valve on the torch handle. With the working pressure set, the welding or cutting operation can be initiated. Lighting and adjusting the torch. With the proper working pressure set for the acetylene and oxygen, open the torch acetylene valve a quarter to a half turn. Direct the torch away from the body and ignite the acetylene gas with the flint striker. Open the acetylene valve until the black city smoke disappears from the flame. The pure acetylene flame is long, bushy, and has a yellowish color. Open the torch oxygen valve slowly and the flame shortens and turns to a bluish-white color that forms a bright inner luminous cone surrounded by an outer flame envelope. This is a neutral flame that should be set before either a carburizing or oxidizing flame mixture is set. Different flames. The three types of flame commonly used for welding are neutral, carburizing, and oxidizing. Each serves a specific purpose. Neutral flame. The neutral flame burns at approximately 5,850 degrees Fahrenheit at the tip of the inner luminous cone and is produced by a balanced mixture of acetylene and oxygen supplied by the torch. The neutral flame is used for most welding because it does not alter the composition of the base metal. When using this flame on steel, the molten metal puddle is quiet and clear, and the metal flows to give a thoroughly fused weld without burning or sparking. Carburizing flame. The carburizing flame burns at approximately 5,700 degrees Fahrenheit. At the tip of the inner cone, it is also referred to as a reducing flame because it tends to reduce the amount of oxygen in the iron oxides. The flame burns with a coarse rushing sound and has a bluish-white inner cone, a white central cone, and a light blue outer cone. The flame is produced by burning more acetylene than oxygen and can be recognized by the greenish feathery tip at the end of the cone. The longer the feather, the more acetylene is in the mix. For most welding operations, the length of the feather should be about twice the length of the inner cone. The carburizing flame is best used for welding high carbon steels, for hard facing, and for welding such non-ferrous alloys as aluminum, nickel, and monel. Oxidizing flame. The oxidizing flame burns at approximately 6,300 degrees Fahrenheit and is produced by burning an excess of oxygen. It takes about 2 parts of oxygen to 1 part acetylene to produce this flame. It can be identified by the shorter outer flame and the small white inner cone. To obtain this flame, start with a neutral flame and then open the oxygen valve until the inner cone is about 1/10 of its original length. The oxidizing flame makes a hissing sound, and the inner cone is somewhat pointed and purplish in color at the tip. The oxidizing flame does have some specific uses. A slightly oxidizing flame is used for bronze welding of steel and cast iron. A stronger oxidizing flame is used for fusion welding of brass and bronze. If an oxidizing flame is used on steel, it causes the molten metal to fall, give off sparks, and burn. Soft or harsh flames. With each size of tip, a neutral, carburizing, or oxidizing flame can be obtained. It is also possible to obtain a soft or harsh flame by decreasing or increasing the working pressure of both gases, observing the maximum working pressure of 15 psi for acetylene gas. For some work, it may be desirable to have a soft or low velocity flame without a reduction of thermal output. This can be achieved by reducing the working pressure using a larger tip and closing the torch valves until the neutral flame is quiet and steady. It is especially desirable to use a soft flame when welding aluminum to avoid blowing holes in the metal when the puddle is formed. Handling of the torch. It should be cautioned that improper adjustment or handling of the torch may cause the flame to backfire or, in rare cases, to flashback. A backfire is a momentary backward flow of gases at the torch tip that causes the flame to go out. A backfire may be caused by touching the tip against the work, overheating the tip, by operating the torch at other than recommended pressures, by loose tip or head, or by dirt or slag in the end of the tip, and may cause molten metal to be splattered when the flame pops. A flashback is dangerous because it is the burning of gases within the torch. It is usually caused by loose connections, improper pressures, or overheating of the torch. A shrill hissing or squealing A flashback is dangerous because it is the burning of gases within the torch. It is usually caused by loose connections, improper pressures, or overheating of the torch. A shrill, improper pressure, or overheating of the torch. A shrill hissing or squealing noise accompanies a flashback, and unless the gases are turned off immediately, the flame may burn back through the hose and regulators, causing great damage and personal injury. The cause of the flashback should always be determined and the problem corrected before relighting the torch. All gas welding outfits should have a flashback arrestor. Oxyacetylene cutting. Cutting ferrous metals by the oxyacetylene process is primarily the rapid burning or oxidizing of the metal in a localized area. This is a quick and inexpensive way to cut iron and steel where a finished edge is not required. Figure 523 shows an example of a cutting torch. It has the conventional oxygen and acetylene valves in the torch handle that control the flow of the T gases to the cutting head. It also has an oxygen valve below the oxygen lever on the cutting head so that a finer adjustment of the flame can be obtained. The size of the cutting tip is determined by the thickness of the metal to be cut. Set the regulators to the recommended working pressures for the cutting torch based on the tip size. Before beginning any cutting operation, the area should be clear of all combustible material and the proper protective equipment should be worn by personnel engaged in the cutting operation. The flame for the torch in figure 523 is set by first closing the oxygen valve below the cutting lever and fully opening the oxygen valve on the handle. This supplies the high pressure oxygen blast when the cutting lever is actuated. The acetylene valve on the handle is then opened and the torch is lit with a striker. The acetylene flame is increased until the black soot is gone. Then open the oxygen valve below the cutting lever and adjust the flame to neutral. If more heat is needed, open the valve to add more acetylene and oxygen. Actuate the cutting lever and readjust the preheat flame to neutral if necessary. The metal is heated to a bright red color by the preheat orifices in the tip of the cutting torch. Then a jet of high-pressure oxygen is directed against it by pressing the oxygen lever on the torch. This oxygen blast combines with the red-hot metal and forms an intensely hot molten oxide that is blown down the sides of the cut. As the torch is moved along the intended cut line, this action continues heating the metal in its path to the kindling temperature. The metal thus heated also burns to an oxide that is blown away to the underside of the piece. Proper instruction and practice provides the knowledge and skill to become proficient in the technique needed to cut with a torch. Hold the torch in either hand, whichever is more comfortable. Use the thumb of that hand to operate the oxygen cutting lever. Use the other hand to rest the torch and steady it along the cut line. Begin at the edge of the metal and hold the tip perpendicular to the surface, preheating until the spot turns bright red. Lightly depress the cutting lever to allow a shower of sparks and molten metal to blow through the cut. Fully depress the cutting lever and move the torch slowly in the direction of the intended cut. Practice and experience allow the technician to learn how to judge the speed at which to move the torch. It should be fast enough to allow the cut to penetrate completely without excessive melting around the cut. If the torch is moved too fast, the metal will not be preheated enough and the cutting action stops. If this happens, release the cutting lever, preheat the cut to bright red, depress the lever, and continue with the cut. Shutting down the gas welding equipment. Shutting down the welding equipment is fairly simple when some basic steps are followed. Turn off the flame by closing the acetylene valve on the torch first. This shuts the flame off quickly. Then close the oxygen valve on the torch handle. Also close oxygen valve on the cutting torch, if applicable. If the equipment is not used in the immediate future, approximately 30 minutes, the valves on the acetylene and oxygen cylinder should be closed and pressure relieved from the hoses. In a well-ventilated area, open the acetylene valve on the torch and allow the gas to escape to the outside atmosphere. Then close the valve. Open the oxygen valve on the torch, allow the gas to escape, and then close the valve. Close both the acetylene and oxygen regulators by backing out the adjusting screw counterclockwise until loose. Carefully coil the hose to prevent kinking and store it to prevent damage to the torch intake. Gas welding procedures and techniques. The material to be welded, the thickness of the metal, the type of joint, and the position of the weld dictates the procedure and technique to be used. When light gauge metal is welded, the torch is usually held with the hose draped over the wrist. To weld heavy materials, the more common grip may provide better control of the torch. The torch should be held in the most comfortable position that allows the tip to be in line with the joint to be welded, and inclined between 30 to 60 from the perpendicular. This position preheats the edges just ahead of the molten puddle. The best angle depends on the type of weld, the amount of preheating required, and the thickness and type of metal. The thicker the metal, the more vertical the torch must be for proper heat penetration. The white cone of the flame should be held about an 1/8 inch from the surface of the metal. Welding can be performed by pointing the torch flame in the direction that the weld is progressing. This is referred to as forehand welding, and is most commonly used method for lighter tubing and sheet metal. The filler rod is kept ahead of the tip in the direction the weld is going and is added to the puddle.